Hi everyone, so today I'm going to show you the proof of Lagrange's theorem. Just for some definitions before we start the proof, the left cosets of H and G. If H is a subgroup of a group G and A is an element of G, then the left coset AH is the subset A little h, where H little h is in H, and AH is a subset of G because AH is contained in G. Also, the cosets of H and G partition G into equivalence classes. An equivalence relation on a set S is a relation R that is reflexive, which means A is related to A, symmetric, which means if A is related to B, then B is related to A, and transitive, which means if A is related to B and B is related to C, then A is related to C, and that's for any A, B, and C in the set S. If R is an equivalence relation on S, then R partitions S into a bunch of subsets of elements related to each other. These subsets are equivalence classes, and every element of S is in exactly one equivalence class. So for an example of how we apply cosets, find the left cosets of the subgroup generated by 3 in Z12. Z12 is the integers modulo 12, which is the integers from 0 to 11. They stop at 11 because 12 modulo 12 is equal to 0, and anything else past 12 can be reduced to a number 0 through 11 modulo 12. Z12 is a group under addition, denoted as follows. So to solve the problem, we get that H, from our original definition of left cosets, is the subgroup generated by 3, which equals 0, 3, 6, and 9. Continuing, since Z12 is a group under addition, we have to use addition to find the additional cosets. So you get 1 plus the subgroup generated by 3 is equal to 1, 4, 7, 10, which you get just by adding 1 to each element of H. Same thing for 2 plus the subgroup generated by 3. You get 2, 5, 8, and 11. Continuing on, we get 3 plus the subgroup generated by 3, which is 3, 6, 9, and 0. But you'll notice that 3 plus the subgroup generated by 3 is the same set as H. So therefore, there are 3 left cosets of the subgroup generated by 3 in Z12. So Lagrange's theorem states, let G be a finite group and let H be a subgroup of G. Then the order of H divides the order of G. And the order of H and G is how many elements are in H and G. So let's begin the proof. Let A be an element of G. Define phi as a function such that phi is from H to AH, and AH is a coset, and phi of H equals A of AH for any little h in H. I'm going to claim that phi is a bijection. So suppose that x and y are in H, and phi of x equals phi of y. Then ax equals ay by definition of our function, and x equals y by left cancellation. So phi is 1 to 1. Now let z be an AH, which is our codomain. Then z equals AH for some h and h. That's by definition of our function. So phi of h equals AH, which equals z. Therefore, phi is onto. So phi is a bijection. Since there is a bijection between H and AH, they must have the same number of elements. Hence, the order of H equals the order of AH. This means that every left coset of H and G has the same number of elements as H. And you'll notice if we go back to the example that we did, every coset has the same amount of elements as H. Since the cosets of H and G partition G, it follows that the order of H equals R times it follows that the order of G equals R times the order of H, where R is the number of left cosets of H and G. So for our example, R would equal 3, since there were 3 left cosets of H and G. Therefore, the order of H divides the order of G, simply because you can do algebra to isolate R and you get the order of H over the order, or the order of G over the order of H. And that's it. Basically, I chose this proof because I really liked learning about cosets in abstract algebra. It was one of my favorite sections. And I like how nicely the proof comes together. It's basically just proving that it's a bijection and then using that to show that they have the same number of elements, and then you just use algebra. The part that gave me the most trouble is trying to figure out how to explain cosets to all of you. I try to do my best, but if you have any questions about them, just comment on the video. And since the whole proof relies on the fact that you need to know what a coset is, it's kind of difficult if you don't understand what a coset is. But yeah, so that's my proof.